So, welcome to the banks of the Mississippi. I won't explain why I'm here, but I think it's important at this point to just reflect on what the different polymers are in the operating theatre and being able to identify the substances that we use on a daily basis. So I'm going to present this lecture on thermoplastics, elastomers, and thermosets. And this is all about understanding the polymers around us and their uses in the operating theatre. So polymers are everywhere. There is a handout on this lecture in the blog section of the website orsicle.org. And as I say, they're abundant in the operating theatre, but for some reason we send them off for high temperature incineration, often when we don't need to, and often when we can recycle them. So the important thing is being able to identify what these polymers are so we know what we can recycle. And generally speaking, the polymers that we have in theatre consist of thermoplastics, elastomers, and thermosets. Those are the three general groups. So I'll start with thermoplastics and I'll concentrate on this because this is what we can generally recycle. Most people consider this as plastics. In the OR, as I say, they're often sent off for high temperature incineration when they can be recycled. They're easily melted, they're easily molded, they can be both rigid or soft, and they often carry a recycling number. And there'll be another lecture talking about identifying plastics and understanding the recycling numbers. So these are the common thermoplastics that we see in the operating theatre. We have polypropylene or PP, which consists of which we will find in syringes, specimen containers, lure locks, vial caps, and needle covers. Many of these never touch a patient, never become contaminated, and can be recycled. We have polyethylene in plastic drug bottles, packaging films, and drapes. We have polyvinyl chloride or PVC, which is in tubings, oxygen masks, and they can be both rigid and solid. We have polycarbonate, often in instrument housing and visors. They're slightly more difficult to recycle. They're very resistant to temperature and they're autoclavable. We have polystyrene, which we see in Petri dishes, lab trays, but also in some packaging. Acrylonitrile butadiene styrene or ABS. In particular, these are on the grey clip-on parts that clip robot drapes to robots, and polyethylene terephthalate or PET, which is a hard, transparent packaging, and that we often see with single-use instruments. I'll show you some pictures of those in a second, but I just need to talk a little bit about polyethylene, which can be high-density polyethylene, which we often see in large sterile fluid containers, such as water and sodium chloride, and low-density polyethylene, which we often see in squeezy bottles and plastic drug vials, such as water for injection. In everyday life, we see polypropylene in food containers, yogurt pots, PET in drink bottles, that's the sort of white, clear drink bottles that we drink out of, LDPE in plastic bags, HDPE classically in milk containers, coffee cup tops have polystyrene, Lego is famous for being ABS, remote controls and game controls are often ABS, and bottles for detergents, washing up liquids, and shampoo are normally high-density polyethylene. There are some other plastics, just to complete the story, that you all have heard of. Polylactic acid, which is classically the filament used in 3D modeling. It's made from corn oil and under industrial conditions can be biodegradable. There's nylon, which is used in machine parts for its sliding properties, but it can also be spun into cloth, and you often have nylon clothing. Polybutylene terephthalate, or PBT, which we see in light switches. It has excellent electrical insulation properties. and then thermoplastic polyurethane, which has rubber-like properties commonly found in phone cases and in footwear. There's also polymethyl methacrylate or acrylic, which is often used as a glass substitute and is transparent. So here is some packaging for a Liger clip applicator. The clear packaging is PET. Here is a hand sanitizer bottle. It's made out of HDPE. You can see the HDPE recycling sign here. And here is a bottle of normal saline or sodium chloride, and that is made out of an HDPE bottle. In fact, the purple top is polypropylene. So then we have the elastomers. They stretch easily. They return to their natural shape when stretched. They feel rubbery. They're heat resistant. And they can be melted down. They cannot be melted down and recycled. So we should try and use as little elastomers as possible. In the operating room, we have the latex rubber in gloves. It's generally from natural rubber trees, and I'll talk a little bit about that in latex allergies on another slide. There's silicone rubber, which we find in drains, urinary catheters, and implants, such as breast implants and testicular implants. There's nitrile butadiene rubber or nitrile, which used as latex alternatives in gloves. And then there's some other synthetic rubbers, which one uses in seals, bungs, and some tubings. Just remember that elastomers cannot be melted down, and we should try and minimize their use, because they all go to high temperature incineration or landfill. In everyday life, we have elastic bands, the soles of shoes, seals and gaskets. Kitchen utensils are made from silicone. You'll find that they don't melt, and that is a property that's used as kitchen utensils. And of course, everyone knows that they're used in Hollywood special effects. Latex can be a natural latex harvested from the milky sap of rubber trees. It's highly durable, it's elastic, and it has some naturally breathable qualities. But you can get a synthetic latex made from a styrene butadiene rubber. It's a petroleum-based chemical. It's more affordable and consistent, but less durable and resilient. And you can get a blended latex, which is a mixture of natural and synthetic latex, often in a 30 to 70 ratio. They say that between 1 to 6% of people get a latex allergy. To me, that sounds like a high number. We know that 6% of people are sensitive or have antibodies, but they don't necessarily have reactions, and reactions vary. There's the IgE-mediated type 1 anaphylaxis, which is supposed to be quite prevalent, but in my whole 30-year career, I've never seen a case. There's allergic contact dermatitis, a type 4 reaction, or irritant contact dermatitis secondary to the chemicals often associated with it, and it isn't really a true allergy. 30 to 50% of people with a true latex allergy also have fruit allergies. So finally, we need to talk about thermosets. They're rigid and heat resistant. They cannot be remelted like elastomers. They are therefore difficult to recycle, and we need to minimize their use. They have excellent chemical resistance and heat resistance. So in the operating theatre, medical adhesives, composite components, some instrument handles, electronic components in medical equipment. And in everyday life, we see them in epoxy adhesives, electrical plugs made from phenolic resin, printed circuit boards, and composite materials. Also, resin molding is made from a thermoset. Resin is a thermoset. So in summary, thermoplastics allow inexpensive disposable devices. They melt on heating. They're recyclable. They're common in the operating room, and examples include polypropylene, polyethylene, PET, ABS, and polycarbonate. Elastomers provide flexibility for tubing and seals. Uh, they do not melt on heating and are therefore not good for recycling. They're relatively common in the operating room, and examples include latex, nitrile, and silicon rubber. Thermosets provide structural strength and heat resistance. They're hard, they do not melt, they cannot be recycled, and examples include resins and adhesives. So that's the end. Don't forget to visit the website www.orsicle.org and to subscribe to this channel. Thank you very much.